Hey guys, welcome back. Let's see if I get set up here. Welcome back to Advanced R Learn With Me, where basically I'm just going through the material of Hadley Wickham's Advanced R book, shown above me, actually. I'm just opening up my environment here. Cool. Last time we ended on the second, we only got through partially the second chapter, and we were talking about the relationship between values and names. So names of objects, these values, and some of the sort of behaviors that happen when you're interacting with different types, or when you're making these sort of bindings. That's getting ahead of myself. I read the vectors chapter today, so I've got types on the mind, but maybe we'll see if we'll get to that content today. Alright, so we'll just dive right into it since, I have plenty to cover, and it's probably good for me to be reviewing and the material as I go. This is to remind folks listening in, this isn't like a teaching people how to, it's a teaching me how to. And by doing so, I hope that people who listen along might be able to gain some insight into some of the material as they themselves tried to work through the content, or develop a deeper intuition about R, and maybe reference some of these chapters. Cool, so copy or modify is the notion that when you change a particular value in an object that's already referred to something, it doesn't, specifically when we're talking about this vector here, it doesn't create, or it does create a new reference, or it creates a new set of values. So it creates a new object where the reference now points to. So recall that X and Y beforehand, they were referring to the same underlying vector in memory. But here, what we're doing here, a little small. Cool. And so what we're doing here then is we're doing the same protocol as before, but now we're changing a specific element within Y, and what we'll notice is that X is the same thing. It didn't change, right? And that makes sense. But Y now created its own object in memory, and it changed this one value. So now Y is sort of rebounded. That's rebound. I guess that makes sense here. And so it's brought back to its new object, and this, think about it, this has implications for when you're writing out programming scripts and you're manipulating references of objects. It could be that you're creating a bunch of copies, and this is actually slowing down computation time. So this is one of the first sort of unique nuggets of knowledge that I'm getting out of doing this sort of dive into advanced R. And so one way that Hadley identifies that we can start looking through some of these structures. One sec. Yeah. Oh. Yes. Sorry. One second. Nice. Okay. Roommates gave me a beer. It is the weekend technically, so cheers to that. I will enjoy this while I stream, I guess. Okay, trace mem. So trace mem is this function that's a base R function that when you call it, it's going to give you some information about the location of a particular object. You call the function with an object, you get the current address. Okay, from then on, if the object was copied, it's going to tell you about where it was copied to. So here, if we change, let's just give it a test, because I know that some of the sort of behaviors in our Markdown document, or at least in RStudio, can slightly vary when you're using these sort of like tracing features. Okay, so for example, looks like it works just fine. And now let's do this and that. And okay, looks like, yeah, so we change the third element of y, and in doing so, it made a copy. So we are able to identify that a copy on modify occurred in this particular instance. And that's going to give us some opportunities to observe when this sort of copy on modify behavior isn't going to occur. For example, if you say change the third again, from here to here, looks like it changed again. I'm actually getting the behavior every single time, so whatever it's saying about untrace is cat. Or here. Okay, so we move here to here. But what about here? So that doesn't make sense. Oh yeah, it does. Okay. It looks like it's just continuously copying on modify. So that's one feature of our Markdown document that actually might be of deficit to us moving forward. I mean, Hadley does talk about this. He says you'll get different results in RStudio. So I am because an environment must make reference to each object in order to display information about it. Okay. But this distortion that I'm seeing while I'm taking advantage of the interactivity of using an R Markdown sort of framework in RStudio, it's not going to directly impact our performance during analysis. You know, I've never used R Markdown or run R straight from R Markdown. I've only ever used R from R Markdown in RStudio. That might be something to explore. Or if people have ideas about how that works, let me know. Reach out, because I would. I've only ever interactively worked with Markdown, R Markdown documents specifically in RStudio. I hadn't really thought about using an R Markdown document that didn't exist in the container of RStudio. Weird. Okay. So we have this copy on modify behavior, and we can follow it. Now, the same rules for copy and modify apply to function calls, and then Hadley supplies us like here, this diagram, which is supposed to, we're gonna get more familiar with these conventions later on, so we don't have to get bogged down into it, but this is like describing the function or the, and how it's interacting with the environment, to which the environment here is contains references to contains these bindings, so these names that have these values that have references to the values in memory, which can also be referred to from other bindings. So that's the idea here. So this is referring to something in memory, and this within the function. Function is depicted in the yellow object on the right in a formal argument A, which becomes a binding in the execution environment. So this is the execution environment. So when a function is executed, it accounts for what is the environment that's being executed in, and then it takes a look at what names in the environment are referring to in memory. Nice. And I just keep massaging in, talking about these sort of specificities of how R handles its content. Yeah. Okay. Cool. That's actually the first time I explained this graph and it made sense. So this is like saying execution environment here, and this is, we're calling that the names of the arguments of this function. This also kind of nicely indicates how there's a difference in environments between what happens in a function and what happens in an environment, and so this sort of is porting over, but this could be a different letter, right? But poured over as this first argument in the function. Okay, so the behavior, let's see. So here's a simple function here where we have a function a and it's just got a in it. We need trace mem. But now notice that if you did some function, nothing, no copy on modify. Why? That's the question, right? There was nothing there. In a regular case up here, we notice we got copy on modify behavior. But here we didn't, so once a function computes x, z will point to the same object. It never gets copied because it's never modified. If a function did modify x, R would create a new copy, and then z would bind to that object. So if something in the argument changed here, to add a 2, so now it's referring right? Huh. Now for self-function environment. Constantly shifting this environment. Same byte code. Huh. I'm curious about this sort of behavior now in Markdown. Anyway. I tried to create some sort of recursive feature to see if when I ran the function, could I force behavior on this binding to create some copy and modify, but it didn't do that. Whatever. Z is now x. So this Z and then Z. Okay, wait. Let me fix this. So the function of x is z is just, since the function doesn't change anything about x, z just becomes x. So this is synonymous to doing a binding that we saw above that was like y. Alright. It's equivalent. Equivalent, at least in terms of the copy on modify behavior. Okay. We'll breeze through some of this stuff now. Another sort of data structure that is, or a vector, we can call it a vector. Another sort of vector that we would want to understand this type of behavior, or how it's a little different, are lists. So lists, and we'll talk a lot about lists later on in the So let's see. This is similar to numeric vector. Similar to a numeric vector above, but how it refers to values is different. So instead of it referring to values as like a single vector, now it has this sort of feature. Oh, I got someone in chat. Hey. Welcome. I'm just talking about lists. Here the name is referring to each of the individual elements and is stored in memory with these individual sort of references. And this makes sense, especially when we talk about later how lists are a type of generic vector that can have different types of elements in their vector. So it would make sense to store them in this way because the contents of these values are potentially going to be very different from one another in a complex structures, really. So let's refer to these things independently in memory. So when you modify a list, instead of this copy on modify behavior, a list is just going to point to a different sort of value in memory, and then it's going to well, it is using copy on. It's actually using copy on modify behavior. Oh no, it says I'm laggy. Oh. Yeah, so right now I'm kind of rolling with the lag, in part because I still need to figure out. Oh, I see. Wait. I'm really laggy. I'm actually. Let me see if I can fix this. Damn, I didn't realize how laggy I was. Okay. Maybe I can. I'm gonna have to mess around with it. I'll make a note. But I recognize, and thanks for the heads up. I recognize I'm really laggy right now. And I think part of the benefit of doing this Twitch streaming is figuring out or debugging a new sort of interface. Like, I can see in OBS I'm lagging. I just don't know what I would do about that. Methods to alleviate that, and I could look that up in real time, but I want to try to get through some content tonight before it gets too late. Thanks for the follow. Oh no, I have to fix that so the follow thing comes. There you go. Thanks for the follow. Hopefully next time I'm not devastatingly laggy when I'm sharing my content. But So this sort of copy on modify behavior happens with lists, but it's actually a little different. And this is the point that Hadley wants to make here, is where instead of copying the entire vector or reference objects, so it's not making like doubles, right? The copy behavior creates this new set of references, binding references to the values, and it's still referring to or bound to like this pool of underlying values. And I mean, the question is, like, if something's not bound to something, where does it go? And that's what we'll talk about in the garbage collector section, where folks are well, the garbage collector section is going to focus on figuring out what happens to the material when what happens to values when they're not referred to by anything. Like, are they just going to sit in memory? That's a reasonable question, and R is smart enough to handle that sort of behavior. Okay. Let's move to data frames then. So data frames, they save data frames, right? As we'll talk about later, they're lists, but they're lists of vectors. Perfect. Oh, nice. Okay, I can do that. See, I'm learning already. Huh. Maybe that'll be better. Hopefully. Okay. I guess I could also just talk louder, and I kind of mumble, if I'm being honest with myself. But data frames are lists of vectors, right? So in this case, like before, it's almost like an amalgamation of the two things that we were talking about. But I wouldn't go as far to say that. I mean, ultimately, data frames are just lists. We'll talk about that later. But here, the data frame is bound to this, in memory, this set of, or this reference in memory that points to the values. So the tricky part about this, and what is gonna create some challenges or some weird copy on modify behaviors later, is that if you modify a column, then the only thing that is modified is the reference value. So that's great, where, okay, I change something about the second column, like I multiply it. Okay, now I'm just gonna create a new vector of values, and I'm going to bind that to the reference in memory, and now that's data frame 2. Great. However, and here's where the danger comes, and you can see this, where like if you modified rows, then everything gets modified, right? So in this case, if I wanted to change something about a row, like multiply it by 3, then my data frame 1 and data frame 3, I'm gonna have to make an entire new copy of all of the columns, thereby generating 2 new reference numbers and this reference. So you can see how memory is really going to get clogged up if I'm doing row-wise computation. And so when you're doing function development in R, or when you're doing sort of manipulation of data frames, which are like the bread and butter of a lot of statistical analysis techniques. It's good practice to manipulate on the column level, or manipulate in such, so if you had to do some row-wise manipulation, make it so that it was column-wise. And this is going to really speed up the computation time on when you're doing those sort of modifications to, I guess, whatever like data manipulation you're doing. But okay, so the last sort of copy on modified behavior that we're going to talk about here is for character vectors. So character vectors are, as shown here, we just have a concatenated vector of characters. We could represent it like this. And there's this underlying, what he's calling a global string pool. So this sort of is confusing at first glance, but just imagine that like as you added character strings to character string values to a particular like R environment, then when you do this sort of binding, it's just gonna always map onto that global string pool that you've been building, which at first glance seems really efficient, right? But I mean, one strange sort of thing that comes out of this are cases like what the picture is demonstrating, where actually there are values in my string pool that aren't being referred to by anything in my environment, or at least currently aren't being referred to by anything in the environment. So some of the ramifications of that might be that you're like clogging memory by having like a very saturated string pool that isn't being referenced or bound to by any names in your environment. But I think that the garbage collector deals with this, so no worries there, luckily. Show references, cool. Alright. This has a profound impact on the amount of memory a character vector uses, right? Because it's part of this big pool. Alright. So it looks like it's not going to be like a big deal anyway, but something to think about. Okay. So let's go through some of these exercises then. The first question then is why traceman 110 isn't useful. I would say it's not useful because we're not doing any bindings, right? So traceman 10 isn't binding anything. It's just creating a vector of values, and then it gives me that in memory. But because I didn't save this to anything, what am I tracing, right? I'm not tracing anything. There's nothing for me to follow in memory because I didn't make any explicit bindings. So that's a good sort of question there. Cool test. Okay, explain why traceman shows two copies. Okay, thanks. Yeah, it sounds like I'm dropping like every frame. Like 90% or 91% of frames. So I'm definitely gonna have to do some investigations about my streaming setup here. I mean, I am using my Mac, but this shouldn't. I mean, it's probably more of a function of my internet quality than anything. So I'll have to play around with that. Okay. Explain why tracemem here in this case shows two copies. Oh, thanks. Okay. So explain why tracemem shows two copies when you run this code. So, and then they actually give us a hint. So we're gonna look at the difference between this code and the code shown earlier. Shows two copies when you run this code. Alright, let's see. So, recall that I might actually have some. There we go. Recall I might actually end up having some challenges answering this question because I'm using R Markdown, and as Hadley mentioned earlier, the R Markdown environment, in order to sort of give it this interactive feel, traces things in memory a little differently. So that's why I was getting this behavior earlier where even though I was doing the same sort of replacement procedure, it was moving it around in memory. And that's a function of being in our studio, but I'm not gonna change up the practicality of using the interface here, at least for today. Maybe in the future. I have to still explore how to use a markdown document, not within our studio, but there are ways to do this. Okay, so here we trace mem, and look, he's asking about this behavior. So not only we're not getting just one change in memory, but we're getting two. So we're able to observe that here. So he's asking why not only do we move from here to here, but then we move twice. And oh, well, that's okay, I get it. In this case, it's because notice that we indicate that these values are integers, right? So we have this vector of integers, but then when we do the copy on modify procedure, we're just inputting a generic numeric, so like a double in this case. So we're learning more about these differences between data structures in chapter 3, but basically what happens here is that we have to do some coercion to the vector, right? So we have to turn these integers into doubles, and then now that the integers are doubles, we make a copy of the binding. So there's sort of there's like a two-step thing happening here. I guess my first question is like, which happens first? Does the coercion of the other values? No, that must be it. It coerces 1, 2, 3 to doubles, and then it takes the doubles, and now we have a 1, 2, 3 as a double, and 1, 2, 3 as an integer, and a 1, 2, 3, 4 double in our memory. That could all be totally wrong, and I'm actually gonna investigate if I'm spot on about that after I make it through the rest of the questions. Because we have 2 more questions here. Okay, so let's sketch out the relationship between the following objects. Okay, here, easy enough. Okay, So here we're doing a simple binding like we've talked about before, where A is being bound to a vector of 1 to 10, and then we're creating a list of two A's. So the list of two A's is just going to look like A, both of which are pointing to the same underlying, or both of which are referring to the same underlying vector here. And then in the case of C, we're going to have three, you can think of it like this again, right? We'll have three little nodes, these green nodes. And then, where are we at? One's going to point to, B is going to point to the list. So I'm not sure how much copy on modify behavior we're going to get. It's going to be cool to see the sketch, but B, this list C, and this kind of gets at this hierarchical structure too, right? Where this list C is going to point to B, A, and 1 to 10. And we know that B points to A. So in memory, then, the A's that this points to are going to be the same A here. And then the 1 to 10, ultimately, that this points to will be the same 1 to 10. But we're going to get a lot. We're going to have multiple of these sort of reference differences in these like reference codes for the three lists. So each list will have its own one of these, but they're going to be pointing to the same sorts of underlying units. Right now I'm calling them units because it's kind of, we can call them vectors, I guess. One thing and another question I'm curious to see the answer about. Cool. What happens if you run this? Before I run it, well, we have a list of 1 to 10, so that, imagine X and then 10 green nodes, or 10 green nodes. And now if you put the X, if you put the list into the second one, I imagine that this now, because list can be hierarchical and a list can contain a list, this puts a reference to X, this reference to 1 to 10, into the second element of the original list. Kind of funky. I'm just going to draw a picture too. But be able to look at this too here. Right, so you guys see the list? See this. Okay, so here we're generating this list, and then now we're creating a new, we're extending the list, and hierarchically we're putting the list into the list. So then we're left with level 1 list and another list which contains the reference to the vector. That's cool. Let's go ahead and take a look at some of the answers then. Okay. Here we go. Okay. Why it's not useful? It's cool. I got that one, yeah. Okay. Initially, the vector x has integer type. Yes. Calls and assigns a double to the third element of x, which triggers copy on modify. Mm-hmm. And you can avoid the second copy on modify behavior. And that would have been a way to test this too, right? Because I just did this. And then this should only give me one copy of modified behavior, yeah. Instead of here, we get the two. Nice. Okay. Oh, and here's that picture I was trying to describe earlier. Okay, so here we have A, right? That was referring to the vector in memory. And now B is this list that points to the, or binds to that vector, but it also binds to that vector. So notice how it doesn't bind to the name. I think that's the hiccup or step I was missing when I was describing the relationship between these, is that B isn't ever pointing to A, it's just pointing to what A points to in memory. So B is reference or bound to the same thing. Curiously, then C points to B, right? And we know that B are these references. And then it also points to A, which we know from the behavior of B is going to point to the reference of A. But in the context of the list, creating a new vector here actually just generates a new reference in memory, right? Are those not the same? Yeah. And you can see there that this value is different than this, right? So what the 1 to 10 that C refers to in memory is different than that of the 1 to 10 that was originally generated here. That, once again, has interesting implications for function development or computation time, because if you're creating or generating a new vector, not doing binding with your list, then it looks like the behavior is going to be copy on modify rather than just like referencing objects. Okay. Cool. Okay, and then here it wants us to right, this is the fourth one. Okay. Reference X binds to the name. So both just okay. Here. So here's the final object. Okay, so X now refers to a list, and in that list we have two different references. We have a reference that goes directly to this vector, and we have another reference which is a reference to the vector. So that's tricky but cool. So the hierarchical structure in this case of the list is making it such that we generate another name or generate another reference from our list by having it the list recursively within itself. And you can imagine then that this could point to another one, which pointed to another one, which ultimately kind of circled around and pointed to the values. But it would just kind of keep these stacks of references. Alright, we're not gonna look at those because we're gonna talk about it. Alright. Let's try to get to the end of chapter 2 today. That's kind of optimal. And then, after I make it to the end of chapter 2 content, I'm gonna mess around with the what are they called? Diff settings. Try to fix my clear lag issues. Okay, you can find out how much memory an object takes using this little function here. So you can see how much a whole data set is. The diamonds data set's very common data set, and you can just also see how much letters. Letters is another data set. So this is letters. Sorry, letters refers to like all the letters. R just has that stored in its pool. Oh, this gets back to that pool of string pool. Letters belong in there. Maybe they're always there. Since the elements of lists are references to values, the size of a list might be much smaller than you expect. So create this big jumbo X, and then you just triple it, and it's not as big as you'd expect. It's only slightly bigger, and part of that is just adding more elements in your list. So adding the elements to your list as this like very small amount. But this makes sense because we're just adding bindings. Not much is being added here. I mean, we're not copying this big structure we made. Because R uses global string pool, vectors take up less memory than you would expect. Bananas. Oh, right, because there's this string pool. Even a vector of banana doesn't take up that much space because R is going to reference banana from the pool. Alright, references also make it challenging to think about the size of objects. Right, so that kind of follows intuition if you think about those diagrams, that the sum of the size of two objects is only going to be larger if the objects differ in some way. So because like what we saw above, x and y contain or refer to or bound to that same vector that we generated here, it's not going to have much of a difference on the combined size of both of them. Right, it's alternative representation. Oh, sweet. So we're even more compact. So basically, we just want to say that's cool. So if R knows that it's a sequence, then instead of saving that large I know. I see chat. Yeah, I know. It's interesting. And that point, you make a really good point, where a lot of when we use R as a programming language is like we do it to solve problems, and I come from a, a background where like in psychology and in biostatistics or in cognitive neuroscience broadly, it's like when you're using a statistical analysis tool like R, you approach learning it or developing skill sets in it in a way that you don't get down to the details of why things might not work or how things actually work behind the scenes. And that's why I'm like circling back to develop an appreciation of the language, because I think that, I mean, practically speaking, there's going to be, I'm going to be a better R programmer and be able to solve those problems more efficiently by having this sort of knowledge. So this, I don't think that at the first stage, I don't think that people should learn this stuff. I don't know how useful all of this would be, especially if you're like an applied programmer. I mean, I just spoke about some of the like practical impacts it could have, but at first stage, and especially if it was your first language, I don't know if knowing that the object size of two objects is only going to be the sum of the two objects if they aren't the same, referring or bound to the same like value. But this is overall interesting stuff, and I'm looking forward to some of the later chapters when it really starts to get into the weeds about some of the technical stuff. It's gonna be really cool. But back to basics. Let's get this chapter out of the way. So, alright, we have some exercises here. Object size Y, object size Y is so radically different. We're gonna have to look at the documentation for this one. Okay. Let's see. So in this case, it tells us that the object size and object size, these two functions, we end up with different sorts of amounts. So the space allocated from object size, remember that these are estimates. Okay, so here we have an estimate of memory. They're both bytes. Oh, perfect. It's not clear cut. So this is a rough indication. So this function is an approximation. But y then I don't have lobster loaded, do I? That's why. Okay. Computes the size of an object or set of objects. Oh, so the difference here has to do with the size of the environment. So it looks like object size is a little more sophisticated, and it's going to try to not double count. Looks like. Yeah, so it looks like object size is going to try to be more scrupulous about what it vets as being part of the size of an object, while object size is kind of just going to give like a larger sort of, it's a base R, base R utility. It's just going to give us like a rougher count, doesn't detect elements unless shared. And seeing it sounds like this is always going to be a little larger than object size y. Cool. Okay. So we have a, we'll call it funds list. 18 bytes. We'll list and we'll list like 3 of the main functions in R. And then it gives us the size, and we're supposed to be surprised about the size. I would guess to say that when you looked at how mean, standard deviation, and variance functions are ultimately calculated, I guess we could do something like this. Like mean. Okay. It's a method primitive. Standard deviation. Variance. Well, we already just saw there were variance. We know that standard deviation is going to just, it looks like really just builds off. Well, of course it builds off of the functions, because we know the relationship between these two constructs, but I guess the sort of confusion about the size, I know mean is very efficiently saved, and standard deviation, but if we peered into the function, we know refers to variance. So in terms of, I don't know how this would look in a diagram, but I'm going to say because standard deviation and variance are going to have a lot in common in terms of the underlying references that they'll make, that the size is going to be very small. So R is being efficient. That could, once again, be cap, but we'll find out. Okay, predict the output of the following code. Object size A here is going to be small, right? Because this gets back to, okay, so object size A will have a value for it, but I think the trickier parts are when we look at these. So list AA, the object size of B then should be 80 bytes, right? Because we talked about an empty cell in a list is about 80 bytes, and the only thing we're doing here is like referencing, or we're doing binding. We're not there's no copying happening here. And with that being said, then this is going to be synonymous in size because they are referencing the same things, or there's no differences in terms of the underlying values, right? This gets to this example we did up here. Here. Object size x plus x, right? Okay, and say if we went into B's lists and we changed both of the lists to 10. Would the size be larger or smaller? I'm going to shoot and say that this is going to make B larger. And then the object size of A and B here is definitely going to be larger because now we're referring to two different things. And then lastly, oh, well, actually, oh, no. Here, because we're changing two things, we're modifying the first element in each of the lists, and we're doing it the same. I think this is going to make this big, but this is still going to be small. Right, because now these are different. So it might be the sum. And now this is going to be even bigger. Or let's find out. I think the last case will be the biggest. Okay, yeah, I got real big at the end there. Okay, so let's take a look. So A, we got some size. B, as we thought, we can actually, let's run this like this. That might be a little easier to see. So object size of A, object size of B. So we have that small increase, right? And that's because those empty lists. Object size of A and B should be the same. Yep. So now we're going to modify the two elements. We're going to do it the same. So it doubled in size. So the object size here, but now the object size is doubled. Why did it double? Well, now it has to do with this copy on modifier behavior. We changed a single element in each of the lists, so now we have to bind, we have to copy and bind to a new underlying vector for each of them. Right, yeah. Oh, that makes sense why it doubles then, because in this case, we're referring to the same thing, but now we're changing both of these, so both of these get the copy on modifier behavior. So now these are two independent ones, so that's why we get the doubling of size. A and B in this case going to be double the size. If it says A and B are the same, so A, we change B. This sort of thing is kind of curious to me. This implies that A and B are the same. They don't have different, well, yeah. They both have lists. They're both lists that refer to values. But notice when we do this, so this is still big, right? Like we expect. But now this is really big. Right, so changing the second element here makes it so that A and B are not the same anymore. Okay, what do we got left? Alright, we got some chunks here, but let's venture forward. I won't skimp on the content. Alright. Object size. Okay, here, see, all three functions are built into base R and stats packages, hence available. What does it mean to measure the size of something in R? There's typically a more general question about what you want to know when you ask the size of something. So here we have the base packages. These are the packages that are loaded into the R environment by default, and we look at all functions. This gives us a bunch of objects, so there's tons of objects that are automatically loaded into R's memory. The size of megabytes per package. Base. I guess the point of this question just to show it's like, look, these are chunky, and what makes it chunky is in part because of the set of like default packages that are loaded when you start R. Predict the outputs. Here's the one. It's 48, double, single, takes this much. So 1,000,000 doubles. Oh. So to just explain like a principled way to do the maths. Here. Contain references to the same memory address. We do that. Here we add the list element container, just like what we said. So when we modify the first element, copy and modify occurs. Both are the same size though. First one gets a new memory address. Right, exactly. So the copy on modify behavior, like what we said, it's doubles. Bye. I'll try to fix the stream next time. It's a little less laggy. Thanks for stopping in. Okay, so the second element of B still references the same address. Is that? So we get the same size. Break that down. We double in size because we have to do a copy on modify behavior, yes. But the second element of B still refers to the same address, so B plus A is the same as B. Because A still refers to B. So we save memory there, but now B is referring to something else, so why? We get the double in memory. So the sum is just what was same, so it's constant, and it's different. So we had that initial plus. So in the, you can imagine if we break it down like this. it'd be this is A and B, and then we have this new other reference B. That's why they're the same. Okay, when we modify the second element of B, this also points to a new address. So that's not going to affect our... It's not going to affect how big B is, right? But it's going to change the relationship of how it's related to A. And so now the size of the object gets wumbo. Gets big. Nice. Okay. Now we've got modify in place. So modify in place, this is the behavior we want to see. We don't want copy of modifies. Or sometimes you can't. Sometimes maybe I'm missing. Sometimes you can't avoid copying it on modify behavior if you want to do a specific type of referencing. But there are probably skillful ways to navigate it, like doing a modify in place. So what happens when you modify an array object? Can you modify an array object without creating a copy? So the exceptions are objects with single bindings, get special performance optimization, and environments, special type of object. Environments are always modified in place. So the R environment that we're in, modified in place. Environments are big. Imagine that if you did a copy on modify procedure for an environment, it would be quite taxing on memory. So that's probably some of the intuition behind why R has it set up to not modify by copying the entire environment. And then since single bindings are very common, we want to save space. So here, same object in memory, but now has different values. Making predictions about when this sort of optimization happens is tricky because I didn't get it to happen earlier. When it comes to bindings, R currently only counts 0, 1, or many. That means that if an object has 2 and 1 goes away, the reference count does not go back to 1. 1 less than many is still a lot. So R is going to make copies. Okay. So it's tricky. Developing an intuition about when you're going to get a copy and place behavior, you're not sure. But trace mem is going to let us explore that. So in this case, we have a data frame, which we're going to make a matrix. Okay. And it's big, and we'll take the median of it. This loop is very slow because each iteration of the loop has to make a copy of the data frame. Right, so x minus medians. So it's going to all the medians, and it's going to take the difference between the data frame and the median for each of the elements in X. The question is, why is this particular loop slow? And this kind of gets at why loops are slow in R, and why we don't really do loops, is because maybe people are behaving using copy on modifies. Copy on modifies is one of the core reasons why, or I wouldn't say core, not like I would know, but it's one of the reasons why loops are hazardous on computation time. In each iteration copies the data frame, not once but twice, but 3 times. 2 copies are made in the brackets, and a further copy is made in the brackets. Down, here. This is a copy, and this is a copy. Here we go. Here's a little tip. Reduce the number of copies used by using lists instead of data frames. So if you're doing this sort of behavior, and I am certainly fall havoc to this, just use a list. I mean, the data frame's a list, right? Why use a more complex structure that is also going to have these properties that make it more susceptible to a copy on modification. Modifying a list uses C code, so the references are not incremented. 1 copy made. So we made X the list, then we did this behavior, boom. 1 line. So when you are initializing your for loops, if you're going to do one, use a list. Especially when you're doing this sort of manipulation of elements within the list. It's not hard to determine, but it's hard to prevent. If you find yourself resorting to exotic tricks to avoid copies, it might be time to write your C++ code. Easy. So if you're getting this long sort of computation time because you can't figure out how to avoid copying from happening, time to go to C++. And ultimately that's one of the features I'm really excited about down the road, because in the sort of work that I do in computational modeling, the time it takes to get estimates for these parameters in these models is a long one. It's a long time. So any sort of break that you can get on computation time is going to be useful, and you should take advantage of that. And I know that writing the code for the simulations or estimation of model parameters could be optimized doing it in C++. So we'll get there when we get there. Environments there's more to be said about environments, and you know what? I'm actually not going to say that much about environments right now to save some time here. But just think of it as environment is unique because it's going to behave differently than other objects in R, and things in the environment refer to these values, and you can have multiple environments refer to an environment, right? Oh, right. So if I copied an environment, it's not going to give me another environment, right? So if I bind an environment to another environment, it won't copy it. It'll change the environment. It's modified in place. So the omnibus, the big environment, is just altered. That means an environment can have itself in it. That's kind of cool. Okay. Explain why the following code doesn't create a circular list. I have an empty set, and the first one we're just going to refer to it. Oh, well, we saw a diagram of this before, where now we have the list, and that list points to the spot in the list. I imagine that this book will have a nice depiction of this too. Hopefully they'll make a nice diagram of it. In this situation, copy on modify prevents a circular list. Let's talk about it. Alright, so we can get the size of the object and we can trace. Copy on modify. Copied object has new memory. List element contains old memory address. So when we refer X to be the first element in the list, copy on modify makes it so that we have referring to multiple things in memory, addresses in memory. So we're not going to get a circle. Wrap two methods for subtracting into two functions and then use bench package to carefully compare their speeds. Okay. Says wrap two methods for subtracting medians into two functions. Okay. So we'll call it sub med 1. It's a function. Okay. And what's it gonna do? It's going to calculate the median of this. We'll call it med. This is one way you do it. Med. And then we'll take x, we'll subtract med. Okay. We'll return this. Let me make this menu. let's be careful here. Alright, subtracted the median. You're here. Install the bench package. Call bench. Alright. Hadley's bench. Alright, so I built out two functions here. Both calculate the median. Yeah, they're equivalent. Both do the same thing. But they might do what they do at different speeds. I think that's the point exercise. Yeah. Oh yeah, I'm supposed to wrap it in somewhere here. Or results. Okay, now I can do summary results. First one was faster.